Show of hands, how many of you have taken mathematics in high school? How many of you enjoyed taking mathematics in high school? How many of you want to pursue mathematics in college? Hi, I'm Anish Chedalavada, and today I'm going to be talking about why I hate mathematics. Or, well, not really why I hate mathematics, but more why I hate the way math is taught in school. Why I think math as a subject is perverse. Now, I love mathematics. On the Facebook page, some of you may have interpreted my topic as a discourse on why mathematics is dumb, but it isn't. It's beautiful. Now, that being said, I don't enjoy doing endless quests to try and find the derivative of x minus 1 whole to the power 1 by 2. I don't believe my sole purpose in life is to score a 7 on 7 in my IBDP Mathematics HL course. And I certainly don't believe that questions 1 to 50, my homework, is going to be the be-all and end-all of my existence. I don't refer to the drudgery that we spew out in examinations. I don't refer to the drudgery that's regurgitated upon us in most classes. I refer to something entirely different. Hold that thought. So, when we're talking about mathematics, I don't believe that solving problems multiple times is something that contributes to my overall well-being. So what we're going to do is we're going to do something a little bit interesting with a very popular mathematical concept in a topic called group theory. Now, group theory describes how one would interact with, say, a collection of discrete objects. These collections are called sets or groups. So there's a very popular concept in group theory. It's called pigeonhole principle. And pigeonhole principle basically states that if I have a set of, say, m containers and a certain number of objects, right? Say every object is the number of objects that would be sorted into any given container is a constant k if it's a multiple of m. Supposing that the number of objects wasn't a multiple of m, then at least in one of the containers, the number of objects would be k plus 1, or 1 more than the average number that would be in other objects. You can see how this may work. If I have, say, 3 containers and 9 objects, then there'll be 3 in every container. But if I have 3 containers and 10 objects, then at least one of the containers will have 4. So it may seem simple in practice, but we're going to do something a little bit interesting with this. So a good friend of mine named Siddhant Mohanty, who currently goes to Carnegie Mellon University studying mathematics there, he gave me this problem that you can see on the board here, which says that in a sequence of n integers, a sequence is a collection of numbers given in a specific order or with a specific rule behind them. There exists a continuous subsequence of integers that sums up to a multiple of n. So in a sequence, I say I have 1 plus 2 plus 3 plus 4 plus 5. A subsequence would be 2 plus 3 or 3 plus 4 or 2 plus 3 plus 4. A summation of a number of terms that are within that sequence itself. Now, the proof behind this is a little bit long, but I'm not going to get into the specifics of it. Because I was lazy, I decided to download this nice screenshot from a mathematical website that describes the same thing, which basically says that since I have, say, n objects, the number of sequences that I can have starting from 1 will be 1 plus 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, and so on until I get 1 plus 2 plus 3 plus 4, etc. n. So that's n separate subsequences I have. And if I were to subtract one of these subsequences from another, I could theoretically create every single subsequence one could get within this sequence of n integers. Now there's n sequences, but if I want to divide these sums by n, then I only get n minus 1 remainders, because if I were to get n as a remainder, then it's divisible. The remainder is 0. So if you look at it a little bit intuitively, you can see how pigeonhole principle comes into the theory. N minus 1 remainders, but n separate sums. So 2 of these sums will have the same remainder. And if I subtract that from each other, that means it's a multiple of n, right? So that's, if you weren't really paying attention during the explanation of this problem, that's fine. It wasn't meant to instruct you. It was more trying to get you to understand a little bit about how the mathematics I'm talking about works, which is mainly proof-based. And it's one of my favorite problems to solve this. I'm sure that if some of you enjoy math, you may find this enjoyable. If you don't, that's fine. So if you didn't understand the problem, I don't care, neither should you. That wasn't the purpose of the problem. It was to try and show you a little bit about what kind of mathematics I enjoy doing. So to make this a little bit clearer, why don't we go to somebody who's actually studied the field a bit more. In 2002, a mathematician by the name of Paul Lockhart wrote a paper called A Mathematician's Lament. It's what my talk is loosely based upon, and it's about why the way mathematics is taught today in classrooms it's degenerate. It's not something that builds to a learning environment. So let's make this a little bit more interesting in terms of analogies, right? So picture a classroom style scenario where there's parallel rows of desks and everybody is sitting with a pen, a paper, and an instrument to calculate the exact angle of a shot or a volley or a kick for football, for basketball, for tennis. And on each of these parallel rows of desks, there sits open a textbook with multiple of the same exact problems with the same exact formulae and the same exact methods applied to solving them. And a student isn't allowed to go out and actually dribble the ball or attempt the shot or attempt the volley. They're just meant to calculate it. Now, it sounds a little bit repulsive and ridiculous, but just follow with the analogy a bit here, right? So the teacher will then supply to these students a series of formulas that they can implement to calculate shots, after which point they will have reached a point where they will considered to be able to be blessed with this magical device that does all the work for them, after which point they only calculate shots, and that's it. There's more complex forms of shots, more complex forms of volleys, better sports to analyze, but there's never actually performance of any of these individual acts. It's always just knowing how to do them. And it's ridiculous. I mean, where would the Michael Jordans, the Pepes, the Sumails, the fakers of the world be today? Like, if not for deviation from the norm, you wouldn't have the game-winning shots we see in most NBA top 10 play videos on YouTube. You wouldn't have your popular NBA mixes set to well-known hip-hop songs, right? How do you expect somebody to learn a mathematical experience or to understand fundamentally how mathematics works if you're not giving them a mathematical experience? See, it's an abhorrent thought. It's what drove Hermione in Order of the Phoenix to start Dumbledore's army, albeit there's no Voldemort out there to kill us all because we're not solving algebra. Now, see, the thing about this is that you're cutting away from a student's internal experience. And while this may seem like an odd analogy to draw, sports and math, they're completely different worlds, right? Well, no, actually. Paul Bennett, he's a high school math teacher, and the thing that's special about Mr. Paul Bennett is that he gave a TED Talk in New York about his students and why they were bad at math and why he thought math instruction was unnecessary. Now, I personally disagree with it. I'm okay with math instruction being made compulsory in schools. It teaches people to look at the world in a different way. But math instruction as it stands today isn't giving students mathematics. It's giving students formulae with which they can crunch numbers. You're not really achieving anything, are you? You're not learning anything. You're not discovering anything. So the reason Paul Bennett gave this TED Talk is because the majority of his students in his class didn't actually understand how to do many problems. They knew how to apply formulae to a certain constricted set of problems, but any minor change in these problems to make them a little bit more interesting, as it were, they weren't able to respond well. So how did he teach them? For one, his major solution was, in fact, he gave his students brain games and puzzles, and he made them solve each of these brain games and puzzles to understand how to grasp the pattern behind each of them. And that's fundamentally what mathematics is about, pattern grasping. It's a way of looking at the world to say, I can talk about this in a particular manner because it happens like this over and over again. I can notice that the number of chairs arranged in this audience row is a certain number because I know the number that are horizontal and I know the number that are vertical. Now, am I going to be given a set of problems about this to understand why it is that this is the case? No, I'm going to be given a set of problems to understand how to compile the numbers of seats in any given auditorium scenario. Now, that's ludicrous. I mean, I'm not actually gaining anything from this, am I? And truly, that's what mathematics is. Now, in your basic adult classes, you aren't going to be taught calculus, you aren't going to be taught trig. I mean, you need to know addition, subtraction, division, multiplication, a little bit of funky financial stuff to deal with and balance your accounts. But beyond that, what? I don't need to find the derivative of anything in common scenarios. I'm not going to be walking into a job interview and asked, hey, find the integral of this individual function or else you won't get the job. So why bother learning it? It seems to be more of a gateway stress into getting into a college, after which point you could get into a job and then do what you want to with the rest of your life. And truly, very few people do go on to use complicated or advanced mathematical topics. I mean, think about it. All the math in your Math 1, Math 2, Math 8 shell, CBSE, ICSE, SSE curricula, AP curricula, SAT subjects, where do you use them? See, that is what I'm trying to hit home, that beyond the scope of computer science or biology or physics or maybe some other natural sciences, maybe some geology, maybe some astronomy, after which point what? Where do journalists use it? Politicians, athletes. That's my point. You don't use this mathematics, so why bother giving people the formulas to these? Now consider a millennium problem, right? Let's break away from this a bit because I'm going on about this a little bit too much. Let's consider this millennium problem. Now a millennium problem is a problem that's considered elite, or it's incredibly hard to solve. Now, the millennium problem is 10 a solitary number. Basically, it talks about whether 10 is a type of number that's considered friendly or alone. Now, a friendly number is a number that has the same abundancy as another number. An abundancy is the sum of a number's factors divided by the number itself. So an example of this are the numbers 30 and 140, which both have the same exact ratio. Now, it's cool, right? Because you can create numbers, you can create correlations between numbers that are seemingly completely unrelated, but actually do have this fundamental relationship between them. And the thing about 10 is we still don't know if there's another number with the same abundancy as 10. It's either doesn't exist, or it's some unbelievably large number we haven't calculated yet. And the thing is, you can't create a computer program that can do this algorithmically. It can only be done by brute force, because it's the sum of a number's factors, which differ from number to number. Now, while that's cool, I'm not really going to use this in everyday life, am I? Maybe in computer science. But beyond that, no. So why am I going to give this to students and say, you must learn what an abundancy is and you must learn this problem in order to survive? No, I mean, it's the same issue Paul Bennett's students had. Why am I learning this stuff? See, you can't expect a student to understand why mathematical concepts are taught if you're not giving them a mathematical experience. See, what Paul Lockhart talked about in A Mathematician's Lament, as seen in the picture over here, is his own exploration of individual identities, right? So in the picture, he's describing a very well-known identity, which is that if I take any quadrilateral, no matter what shape, size, angle, length any of the sides have, if I join the midpoints, it's always going to be a parallelogram. That's a conspiracy. Why does this happen? I mean, it seems so baffling, right? That you're always going to end up getting something so perfect inside something that isn't governed by rules that we can define, besides the fact that it's four-sided. It's cool, but I'm not going to force you to learn the proof. I want you to enjoy the fact that it's cool. And we are in a system that's comfortable with zero accountability to a person's interest, but is comfortable with accountability to a number that appears on a card based on how well that person can by heart and apply a formula. That's not mathematics. So similarly, if I knew that 3 years ago my friend's sister was 5 times as old as she is now, or whatever, where would I get that kind of information? I'd be arrested before I had the opportunity to even figure out what the person's age was. So what most of us fail to understand is that mathematics fundamentally is something we pursue as an interest. Most mathematics these days wasn't actually developed while studying math. It was developed while studying other things. Calculus was developed to understand mechanics, things like that. Now, while this may not be true, and it's a bit of a generalization, For most cases of school-level mathematics, the reason we learn mathematics has never actually been given to us, but we can implement it in other subjects if we so choose. I used it in economics recently to understand how demand and supply curves change, and I found out that there's actually an entire field behind this, which may sound a little bit naive in retrospect, but I mean, we were never taught that in economics. See, mathematics was, and will always continue to be an interest like art. It's the same way Lockhart described if you were to teach art by giving somebody a color by number kit and then say in number 1 has to go purple and in number 2 has to go orange, and you are never supposed to deviate. Where would we have Van Gogh? Where would we have Monet, Manet? It's the entire segment of art that's just been deleted because you want somebody to form something in their heads that is rote and not based on discovery. Like I said earlier, we're accountable to the mark and not to our own interest. And see, that's what we've developed math for. It's something we do to pass time. But that doesn't take away from the beauty of math itself. Pattern recognition is anything but mundane. If any of you have ever solved a Rubik's Cube or solved a puzzle, your basic jigsaw puzzles, you'll know the exhilarating feeling of discovering something, of solving something. And solving a Rubik's Cube, finishing one of those 15 square puzzles to create a certain arrangement of numbers, that is all math. So what is this implanted in our heads that's created to hate mathematics because it's just based so solely on rotely solving the same problems? See, personally, I've never gotten full marks in a mathematics test because A, I don't care about computation, and B, should I be inclined to solve a computational problem, I have a calculator for it. Now, let's talk about these formulas. If you could give me the Taylor polynomial for sin x, or if you could give me the unit circle for a trigonometric identity, right? Right at this moment, if I were to give you 2 A4 size papers, would you be able to do it? No. Define the Ahulya equivalence for me. It's non-existent. I just made the Ahulya equivalence up. It's named after a friend of mine. See, remembering these formulas, it's like trying to remember the names of the 2016 Democratic Party candidates, which, as Cicely Strong pointed out, is nearly impossible to know. But give a person the tools with which to prove something, and then, my friends, you might have the beginning of potential discovery at your hands. If you were to give somebody the method by which to prove the product rule as opposed to giving them the product rule, maybe they'd remember it. See, the reason I do well on math tests, well, never scored full, but I've never, ever gotten below an A+, except maybe on occasion. But the reason I managed to score well on math tests is because I self-study at home. It's not because I'm naturally gifted, though I'm not denying that I am. It's because most of these things that are given to us axiomatically are theorems, which I then go on to research about. And that's what a real mathematical education should entail. Through investigation, not spoon-feeding, that's the way one learns. That's what you would give somebody if you want them to truly have an experience, to explore their own intuition and see, I have a hunch. And let me go just look into that hunch a little bit. Let me look at this relation. And see, that's what a class should be like, where a student, instead of being told to go look it up himself, is given the benefit of the doubt and explored. Now, the official diagnosis for something known as math anxiety exists. And that's entirely system-introduced, because like Natalie Portman in Black Swan, one becomes absorbed with this role of memorizing formula after formula till they become memory robots devised to apply the same algorithm to the same thing. We're computers, not people. And you're killing a person's curiosity and intelligence. Now see, there are systems that do try to implement learning of math through, say, investigative reports, like the curriculum I'm currently studying, which is the IBDP curriculum. And I have the benefit of having an amazing teacher, but Not all teachers are like this, because some of these amazing teachers themselves can't give a student the kind of mathematical experience they'd want to. Because if you want somebody to actually learn, they're not going to pass. It's entirely the system that we have to blame for this, which is one person should be able to understand how to apply a formula to a problem that they see. And I'm saying this a lot, but my God, does it annoy me. And so when you have teachers that do this, incrementally, the number of people that have had a mathematical experience goes down. And more people who've had math anxiety will become more teachers and introduce this math anxiety to students because they themselves don't fully understand what they're teaching. And I have been in a classroom like this. Personally, this has killed a lot of my problem-solving ability. Currently, I'm struggling to solve some of the most basic problems that I have tackled as a 7th grader or an 8th grader. And not problems in school, but actual proof-based problems, like the pigeonhole principle problem I was giving you earlier. Now, when you are to do this to one person that loves math this much and that has gone on to do this themselves, I'm not trying to brag here, but not everybody has the time to go home and study mathematics because they're busy studying other subjects. So people that want to major in math, that want to investigate math, that want to become scientists, artists even, that goes down. And 50 years down the line, we lose mathematical minds. Can you imagine the diagnosis existing for art anxiety or music anxiety? That's ludicrous. And that is why I hate math. Thank you.